So, we're going to learn about, well, first we're going to start with irrational numbers. Well, we're going to start with radicals, and we're going to talk about more irrational numbers. I'm going to be brutally honest with you. It's very abstract. So my idea here is to make it as simple as possible for you guys and girls to understand it, so that when we get into the assessment, you'll just be able to bang through it, okay? The first thing we're going to start with is we're going to actually start classifying numbers, okay? We classify numbers way, way back when they started actually physically writing out numbers and figuring out what these values even meant. They had classifications for types of numbers that we had in, I guess, our civilization. Okay? I'll make this a little bigger so you can actually see it. The first set of numbers that we dealt with, or the first classification, was what's called a natural number. When they first started counting, they basically labeled, they had 1, 2, 3, 4, and on and on and on. What do you notice about that sequence right here? It's increasing by 1, that's significant. Okay, why not? Oh no, I'm on. They're all whole numbers. Good, so there's no decimals. Okay. What number did I start with? 1. What's the number below 1? 0. What happened was at this time, when they first started determining classifications of numbers, they didn't have a number that represented nothing. Okay? We know that a number that represents nothing is what? 0. So they first started with natural numbers. They said, "Ooh, okay, we need something that classifies a 0. So they moved into whole numbers. Whole numbers, same sequence, 1, 2, 3, 4, and so on, but they added a 0. Okay? So that represents, it had something that could represent nothing at all. Okay? Now, what is less than 0? What's a number that's less than 0? Negative 1. Any number with a negative. They didn't have a classification for numbers that were represented as a negative. Or basically, in your real times, if Levi owed me something, that was represented as a negative. He owed me, like, with regards to currency, if it was like $100 or $5 or $10, whatever, there was no representation as to how that looks. Okay, so then they came up with negative numbers. So again, same sequence. We had 0, we had 1, we had 2, we had 3, 4, and so on. But now we added negative 1, negative 2, and all the way that way. So at this point, they've classified natural numbers as whole numbers from 1 to 5, or 1 and up. Whole numbers included 0, still no decimals. And then we have integers, so we can represent negative numbers. Okay? With me so far? After we've got integers, the next question that they had was, how do I represent half of something? A third of something? A quarter of something? They determined that we needed what type of numbers? What are those numbers? A half, a third, 0.5, 0.75. What type of number is that? Starts with a D. It's a decimal. They had to classify something to represent a decimal. Okay. Now they had 2 different types of decimals. Okay. We have a half, which as a decimal represents what? 0.5. So if I wanted to do my number line, I would have negative 1. I could have negative 0.5. I could have 0, 1/2, and 1. Okay. Those decimals or those fractions, they stop, right? After 0.5, what's the number after 0.5? For a half, 1/2. It's just 0.5, right? Is there any other number other than 0 after 0.5? No, it's just 0.5. Whereas if I gave you a third, if I got you to write that as a decimal, how would you write it? There we go. 0.333333 going on forever. Okay? We don't know if it goes on forever. We don't see a pattern. We just know that there's a bunch of 3s. Okay? That make sense? So, are there any other numbers that we don't quite know the pattern for? So, right now we've got rational numbers were decimals that had a fixed ending. So, 1/2, 1/3, or sorry, 1/4, 2/3, not two, I keep going back to the third. 1/4, 1/5, anything that has a set, like it's 0.5, 0.25, 0.75, 0.1. It's a terminating decimal, yeah. Okay? Irrational numbers, or irrational fractions, go on, and on and on and on and on. What other numbers or symbol is there that goes on and on and on forever? Pi. It's another type of number. What we're going to start talking about today is we know that the square root of 4 is equal to 2, correct? Okay, we're going to talk about that later today, but what happens if I have a number like the square root of 5? Can anybody tell me what the square root of 5 is as a decimal? Is it going to be a decimal that terminates? Probably. How many people say yes, it will terminate? How many people say no, it's going to be a nasty number? You're allowed to think outside the box, and it's okay. I'm not going to laugh at you and be like, oh my god, Daniel actually thought that it terminated. No, it's fine. It goes on and on and on. It's a weird number. There's no pattern. It's not repeating, but there's no set terminating decimal. So it will be an example of an irrational number. So any number that goes on forever or has no set pattern and it just continues on, those are what's called irrational numbers. So up to this point, you've got so many different classifications that you're like, holy crap, there's so much there, right? A lot to remember. So finally, mathematicians said, you know what? Let's just have one classification that covers everything, encompasses all of the numbers, and then they came up with just real numbers. And those are literally any kind of number, from fractions to decimals to whole numbers to integers to negative numbers, you name it. Give me any kind of a number. Give me a number. 1. 50. Give me some decimals. 0.86, 9, 1. Give me another number. Give me a negative number.
Negative
679. 1738. Okay? Those are examples of real numbers. Okay? Any and all numbers that go from this classification of numbers. Make sense? Anybody not get it so far? Okay? The biggest ones that we're going to deal with are irrational today, but just recognize that these are out there and that each one has a specific difference. Okay? So a natural number are what types of numbers? 1 and above. And are they whole or decimals?
Whole.
Okay. What about whole numbers? What's the difference between a whole number and a natural number?
Whole number includes 0.
The whole number includes 0. So as we go through this, actually I'll do that after. So whole numbers has 0. What's next? Integer. What's the difference between a whole number and an integer? Negative. Rational numbers? Decimal. And what type of decimal? Terminates, like 0.5. Irrational, doesn't terminate, goes on forever. And a real number, all the numbers. Okay? There's a graphic that you need to see and that you need to be aware of, and it brings home that point that we just talked about, the differences. Okay? And it has the symbols for each term. So a natural number, they classified as an N. Okay? They represented with the letter N. Okay? So we start with the letter N, we start with natural numbers. Okay? After that we had whole numbers. The big difference between whole numbers was that a whole number can be a natural number, but a natural number can't be a whole number. Does that make sense with this visual right now? Okay? The difference being with 0. Okay? A whole number, some whole numbers can be integers, but not all whole numbers can be integers. The difference between a whole number and an integer is that negative. Okay, not all integers can be rationals. Don't ask me why it's a Q. I'm not quite sure. Basically, they needed a letter because real numbers took the R, so they gave you Q. Okay. Rational numbers can be integers, but can all integers be a rational number? No. Okay. Next one, Q with a hat, is irrational numbers. That doesn't look like a Q with a hat. Okay, and then finally the last one was the real number, and they classified it with the letter R. I don't need you to memorize the letters or the classifications, but when we get into 20-1, 30-1 math, they're going to start wanting you to know specifically, really it's a lot of the natural whole integers and real numbers. Those are the big ones that you're going to recognize and see more often. Okay? But what this graph represents is basically that a real number encompasses everything. So you can go inside the circle, but you can't go outside the circle. So a natural number, not all natural numbers are whole numbers. Not all whole numbers are integers. Not all integers are rational, and so on. That make sense? Good? Alright. So that's where the classifications of numbers came from. We're going to specifically work with irrational numbers today and introduce those. So just very quickly, I want you to tell me what types of numbers, or what classifications you would use for some of these numbers. So the first one, 4.87, what would you say that type of a number is?
Rational.
The rational. Is there any other ones that you would call?
A real.
A real number? Oh, sorry, rational and real. Absolutely. First off, could you say that every single number here is a real number?
Yes.
So I should see that in every single one, right? Why did you say it's a rational number? Terminates decimals. Good. What about pi? Pi is a real number and irrational. Right? Because it goes on, we still don't know. Now, there's a debate right now about whether or not a number is a real number or a rational number or irrational. To this day, we don't know if pi terminates, or if it repeats, or if it loops, or what the pattern is, right? We just know that as it stands right now, people are still researching to find out what that last number in pi is, right? We just assume that it's 3.14, but we do know that it goes on and on and on, right? They haven't found out, but tomorrow, right now, they could determine, hey, it actually stops here, and here's the pattern. It could be a billion numbers long, but there still could be a pattern. Okay, there's a debate that you could make that every rational number could be irrational, or every irrational number could in fact be rational. Right? So just keep that in mind as we go here. Root 5. Rational, irrational, real number, what type of number is it? It's a real number. Also what? Irrational. Why? Because as it stands right now, we don't see a pattern with the square root of 5. Okay. Put that in your calculator, you get a crazy decimal. Now, what type of a number is 0? It's a real number. It's a whole. It's a integer. It's a rational. It's a irrational, and it's a real number. Right? Why could you make the debate that 0 could be a rational or it could be an irrational number? Did I? Sorry. My bad. You are right. Why could you make the debate? Anybody? Right? I could go 0.0 forever. Technically that's a repeating decimal. And then my terminating decimal would just be 0. What type of number can 0 not be? What's the only number that's a natural number? Good. Negative 9.4 repeating. Real. Integer can't be y. Why can't it be an integer?
it's an irrational.
Because it has a decimal 4 and it's irrational. Good. Okay, 24 divided by 3, or 24 over 3 is? It's a real number.
Is it
It's equal to 8, so what's 8? 8 could be whole, it could be natural, it could be integer. Alright, is it rational or irrational?
rational?
Because it terminates. Good. And then this one here was real and irrational. Okay? You're not going to get 100 million questions that say, hey, classify these numbers, but just recognize the different characteristics. Okay? Good with that? Mariana? Yep.
How is one bottom irrational?
How's what?
The decimal bottom irrational.
How is decimal 1 irrational?
The decimal that you put irrational for?
This last one?
Yes.
How is it irrational?
There's no
Sorry, you can't see it, but there's dot dot dot. It would assume that it's just like pi. It goes on and on and on. They haven't found a set terminating point. It's not saying that it couldn't be there. As it stands right now, it's not. That make sense?
Yep.
Sweet. Good question. All right. Let's break down specifically. Let's talk about radicals. Where, Ryan, have you seen radicals so far in this course, in this class? Where have we seen a radical before?
A radical?
Yep.
I'm not sure what that is.
Well, good. We're learning about it today. This works out. An example of a radical would be something like this. Where have we seen that so far? Square root of 4. We've done it a couple times this semester, for this year.
The mentioned thing.
Polynomial, not so much, oh yeah, we've done a little bit of polynomials, but we've also done it with trigonometry. When have we had to use a square root function? What is it? Area,
Trigonometry.
yeah. What part?
Pythagorean.
There it is, Pythagorean theorem. If we're looking for a side length, we can take the square root function. Okay, we're going to actually dissect and break down what a radical looks like and what the different components are. We have a little, basically, a check mark, which is called the radical itself. And you've got, we're going to talk, this doesn't do it justice, but we actually have 3 different types, 3 different definitions, or 3 different labels. Okay, the example here inside of the check mark is what's called the radicand, that's inside the radical. And we have a little number, sometimes we can have a little number inside the little check mark, and that's called the index. If we don't see a number here, we assume what type of a root is this? Square root. If we see a little 3, it's called a cube root, a 4 is a 4th root, a 5 is a 5th root. Okay? What that index represents is how many times you have to multiply a number to get what's inside the radicand. Okay? I'll do an example to show you what I mean. But we also have another number sometimes we can see. So for the example, we could have 4 to the cube root of 5. Okay? We know, where's my index? What number is my index? 4, 3, or 5?
3.
3. Which number is my radicand? 4 or 5? 5. Okay? If I told you that this was actually 4x, what would you tell me the 4 was called? What is this? The label. Such as a C. Coefficient. Number in front of a radical is called a coefficient. Make sense? So just keep that in mind when we start talking about mixed radicals, that we do have another component. Sometimes it's called a coefficient. Right? So we have these sets of different types of numbers, or different types of roots, and basically what that means is whatever number I'm taking, if it's a cube root, square root, 4th root, I'm taking a number, finding a number that if I multiply it by itself, however many times it gives me the number inside. So let's do an example for each one. If I have the square root of 49, what 2 numbers multiplied together gives me 49? If I multiply it by itself, 7. I know 7 works because 7 times 7 is equal to 49. Now, what if I do the cube root of 8? What does that represent before I get the answer? What am I looking for? Fantastic. A number multiplied by itself 3 times gives me, what number am I looking for? So a number that multiplies 3 times gives me the number 8. What is it? 2. 2 times 2 is 4. 4 times 2 is 8. If I have the 4th root of 16, what is this telling me? What is this asking me? Same thing, except now it's asking how many times am I multiplying it by? 4. So I'm looking for a number multiplied 4 times by itself to give me 16. What's that number? 2. Okay. 5th root of 32. Do you see a pattern here? I know this because if I wanted to prove this, I would go 2 times 2 times 2 times 2 times 2. That'll give me 32. Fair? We'll break down how we know these when we are actually showing you how to. Actually, well, we did a little bit of this. If I wanted to take 32, I would take my factor tree. Who can tell me how to break down my 32 into factors, into my prime factors? 8 and 4. Neither one of these are prime. 8 breaks down to 4 and 2. 2 is a prime number. 2 and 2. 2 and 2. Right? Good? Alright. Having said that, I can now rewrite the 5th root of 32 to actually equal the 5th root of 1, 2, 3, 4, 5 2's. 1, 2, 3, 4, 5. Remember whenever I was asking about how do you know a number is a perfect square or a perfect cube, you're trying to find groups of 2 or 3 depending on what you're looking for, right? If I'm looking for the 5th root, what groups of what am I looking for? Groups of 5. Do I have a group of 5? Yeah. I've got 1, 2, 3, 4, 5. All of that comes outside of my radical. Is there anything left inside this radical? No, so it goes away. And I have 1, 2. Does that make sense? We're going to talk about this when we show you the difference between a mixed radical and an entire radical. It'll make a little bit more sense why we do that. Okay? But that's the long version. Like, you can do this all in your calculator to give you the same answer. This is the long version for it, okay? Good? Alright. Is everybody good with the differences between what a square root, cube root, 4th root, and so on? Alright. So now, I believe the next piece is breaking down that not only do we have positive answers, like we know the square root of 16 is what number? Square root of 16 is? 4. I know that because 4 times 4 gives me 16. Is there another number that if I multiply it by itself, it will give me the answer number 16? Think about it for a second. -4. Good. If I take -4 and I multiply it by -4, what number do I get? Positive 16. That works for all of these. So don't be, when you see a square root function, think about it like this. You should always have 2 sets of answers. One should be the positive answer, 7 times 7, as well as, oh, I just get a message. -7 times -7. Make sense? Okay? Now I'm going to pass out markers, and I want you to actually think about why the square root of -16 does not work. Okay? You can brainstorm with your table or by yourself, but I want you to try to figure out why the square root of -16 does not work. Alright? You want to write it down or do you want to mark it? I want you to tell me why -16, the square root of -16 does not work.
The 4 and the -4 is different.
Think about it.
Is it because 4 and the -4 is different? Like, you're repeating team. Once you repeat the team. See how you have feet, right? Oh wait, no.
What's the whole premise of a square root? What's the whole idea of a square root number? That they're the exact same. Can you have a number that is the exact same as the other and come up with a negative number? No, you can't take any number, multiply by itself to get a negative number. Okay? So for square roots, this does not work. You can absolutely have the negative square root of 16. That will give you your negative 4. But you will never find a number that two positives always make a positive, two negatives always make a positive, a negative and a positive gives a negative, but those aren't the same. For example, 4 and negative 4 are not the same number, correct? Having said that, prove to me yes or no that you'll get an answer from the cube root of negative 8. Can you get an answer for cube root of negative 8? Actually, put your phone around the desk.
No, it's very long. Negative 2,
Are you Googling it? Nice.
Hey,
Yeah, you just be careful.
I'm 30.
Dumb.
I would bet my 6.
Okay, yes or no? Does the cube root of negative 8 give me an answer? How many people say no? Put your hands up. Hands up if you think no, this is not an answer. You're giving me some tomfoolery here, Mr. Dillon. How many people say yes, you will get an answer? What is said answer? Negative 2. If I take the cube root of negative 8, I will get an answer of negative 2. If I multiply a negative number an odd amount of times, will I get a negative answer? Yes. How many times am I multiplying it in this example? 3 times. Negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. So guys, girls, just be careful. Be careful with this rule. With the square root, a negative number inside the radical, Mackenzie, doesn't work. But a negative number inside the cube root could work. Not saying it always will work, but it could. Fair? Make sense? Alright. So now let's start talking about different types of radicals that there are. Okay? The big difference between an entire radical and a mixed radical, what do you guys notice? Just looking on set here, what's the big difference that you see between a mixed radical and an entire radical? Mixed radicals have a coefficient in front. Okay? An entire radical will have no number in the coefficient, which just assumes is 1. Okay? Whereas a mixed radical will have a number as a coefficient. Now, how that coefficient comes out, we just showed in the last example. I know that, for example, cube root of 27 can actually be written 3 times 3 times 3, correct? If it's a cube root, how many groups of what am I looking for? I'm looking for groups of, for a cube root, I'm looking for groups of 3. Do I have a group of 3? I actually have a group of 3 that is a 3, right? For every group of 3, I write down the number once and I put it in front of the coefficient. Here's my issue though. I have my coefficient, I have my square root, which is now 0, there's nothing there. This just goes away, which equals 3. Makes sense? Yes, no? They may not get what I just did there. Again, if you just simply go to your calculator, with cube root of 27, you'll get 3. That's how we work with an entire radical, is that everything is inside the radicand. Basically, these mixed radicals have the coefficient in front to show that it's been simplified. In your math outcomes for this year, you need to know how to convert a number that is from entire, as an entire radical, into a mixed, and a mixed number, or a mixed radical into an entire radical. We're going to show you how to do that because it's basically similar to what we did with factoring polynomials. You're just working backwards. Okay? So, let's start with entire to mixed radicals. Give me an example of an entire radical. Any number at all. Let's make it an even number. That makes 42. Awesome. Perfect example. Square root of 42. Here's how I break that number down into an entire radical to a mixed radical. My first step is always my factor tree. Who can give me the factor tree of 42? Six and seven. Seven's a prime number. Huh? 3 and 2. Alright, this isn't going to be the greatest example, but that's okay. Okay, why is this not going to be a good example? If I rewrite this, 3 times 2 times 7, I get 42. My problem is, do I have any, if it's a square root, what am I looking for? Groups of?
Same number.
How many have the same number? 2, 3, or 4? 2. Do I have any groups? No, doesn't work. Okay? So this is actually, I can't break that down into any simpler form. Let's try a different example, one that I know will work. 96. Break down 96. 96 breaks down into what?
48.
48 and 2, good. 48 and goes down to 2 and 24. 24 goes to 2 and 12. 2 and 6. And 2 and 3. Alright, we got tons of numbers here. We're going to be able to break this down. I can rewrite the square root of 96 now into its prime factors. So I can write the square root of 96 into, how many 2's do I have here? 5. 1, 2, 3, 4, 5. And how many, do I have any other numbers? 3. Alright. Now, it's a square root function, so am I looking for groups of 2? Do I have any groups of 2?
Yeah.
How many? I have 1 here, I have 1 here. Do I have anything left over? I have 2 times 3 left over. That's going to stay inside the radicand. What are these two pairs going to do? They're going to go out. Okay? For every group, it actually works out like this. 4 times 4 times 6. What's the square root of 4? 2. So 1, 2. Bless you. 1, 2 comes out. What's the square root of 4? Another 2. So I have 2 sets of 2. What's 2 times 2? 4. What did we say was left inside the radical? 6. So that what's happening is that I'm telling you that the square root of 96 is equal to 4 root 6. Here's how I can prove it using your calculator, Ryan. If I go to my calculator and I take the square root of 96, I'm going to get a decimal. 9.79795891. If I take, what was it, 4 root 6, I get the exact same decimal. Okay? There is nothing different that you're doing. You're literally just rewriting the answer so that it's in simplest form. Just like when we break down fractions into simplest form, you're doing the same thing when you're going from entire to mixed radicals. Yep? Yep. Okay? Make sense? Is everybody good with that? Alright, with the markers that I've given you, I want you to break down the cube root of 92. I want you to tell me what that is as a mixed radical. Right? Cube root of 92. I'll leave this up here for you so you can kind of have something to base by. Cube root of 92. All right, let's go. Yeah. Okay. So what this means this part here can actually be removed. No, it wouldn't work. It would still be I do. I know that you do.
Stop waiting.
Wow.
I don't feel it either. I'm feeling it. You do you.
Okay, maybe.
See, basically, once you figure that out, because you can just check it yourself.
Oh, what? No, we're
Good.
trying to play backwards. I understand these things.
This is good. It's not going to work out. Does 92 work out? Doesn't. Okay, go cube root of 96. Cube root of 96, try that. Cube root of 92 doesn't work for you, I apologize. Do the cube root of 96. That one definitely will be because it only is 2, 2, and 9.
Please.
Okay, 96, my bad. 96 will definitely work. Okay, I want you to try it. Factor tree. You both know how to
No,
factor.
you did not ask for it from creativity.
Yep.
You don't just throw it at it.
Yeah, you're not going to be able to rely on your calculator. You can actually use that to check your answer. But, that's why I wanted to even show you this, okay? First part of this year, I told you which is more accurate, decimals or fractions? Fractions. Decimals are not accurate, okay? Because eventually, especially with a repeating decimal, you have to stop eventually, right? If I want to write 1/3, I could either write as a decimal as 0.3 repeating, which is the cap really does help it, but if I had to write the whole thing out, I'm going to go on and on and on. Whereas I write 1/3, it's more accurate. All of these these radicals that you're dealing with are crazy decimals. Okay? This decimal does not just stop at 1, it will go on and on and on and on and on. The reason why we have simplified or mixed radicals is so that it gives me an accurate answer and it's simplified. It's more accurate. Okay? That's why we're doing this. It's representing that there's more than just decimals in our world. Okay? So that's why we're using this. So now what's the difference between what you're doing now with your cube root and your square roots? Prime groups of 3.
Then it's 6. Square root of 6.
Nope, it's not 6. 2 times 2 is 8.
8. Jeez.
Cube root of 8 is. Cube root of 8 is. 2. So what is your final answer? 2 with the cube root of what's inside? 12. If you did not get 2 to the cube root of 12, you need to raise your hand and show me what you did. Oh, you're close.
Oh, I get it now. Finally, the whole library.
Yeah, pretty good. Keep that 3. Okay, how many groups of 3? How many groups of 3 do you have?
What procedure are you?
What? Just 2.
That's a week. But then you get faster to steam it.
So inside the radical, it didn't go away.
Well, people that have right now the highest level is 688 by like a normal steam. They only share 1.5.
Right one.
Like one guy pays on for 8 hours, sleeps, another guy pays on for 8 hours, sleeps, another guy pays on for like 6 8. And right now currently they stream. They're really entertaining. Sometimes you don't stream and it's time it's like stuff like children. Like you're you can watch it at like 2 years.
Okay, everybody good? No? Do you need another example? Okay, let me show you. So I'll show you how I get this answer, guys and girls.
So would be
Just listen up.
would be good there.
First step is what?
Like 2 and 2
Jansen, what's my first step?
what?
Factor tree. 96 breaks down. We actually just did it already, right? So we can actually break it down. How many 2's are there? 1, 2, 3, 4, 5, and then an extra 3. Because I'm looking for cube roots, what am I looking for? Groups of?
3.
3. How many groups of 3 do you see? Just one. I have a group of 3, and it is 3 2's. 2 times 2 times 2 is equal to what? 8. What is the cube root of 8? 2. This whole sequence here cancels out and becomes 2 on the outside because the cube root of 8 is 2. What am I left with inside the radical? 2, 2, and 3. Can I do anything with that? Can I pull it out of the radical or no? No. What's 2 times 2 times 3? 2 times 2 times 3 is 12. Guys, stop. And I like leave with my 2 in front. Okay? The hardest part of this is figuring out what factor tree, or basically figuring out the factor tree, the prime factors of the number you're trying to work out. That's the longest part. Because then after that, you're just determined, it depends on what cube, if you're looking for cube root, square root, fourth root, fifth root, and so on. Do you guys girls want another example? Try? Alright, I'll give you another square root example. It's a little bit easier. Let's do, have we done 48? We haven't done 48, hey? Try 48. Wait, you just did 48. Let's do, let's go. Let's do 32. 32. Okay, show me 32. Square root of 32 as a mixed radical. What? I had to acclimatize myself. I was getting myself up a little earlier so I wouldn't be able to. Right, it should be my mad face if you don't try this question. Okay, good. So now do your square root and then put all your prime numbers that you see here. Don't open it, don't open it. Don't open it. How many two? Yeah, you can. With 5 numbers.
Dude, I'm not supposed to
That makes sense? Okay, try this one. Try this one. Square root of 32.
We're doing 32.
Ryan, what was the answer? 4 root 2? If you do not have 4 root 2 as your answer, you have something's up. Okay. How can I check to make sure my answer's right? Well, I can put it into my calculator just because I know. I got a good feeling. I can put it into my calculator to check. Okay. Break down 32 into prime factors. Stop. Now, once you're on your calculator, when I ask this on the test or on your assignment, I'm going to say I need to see the geometry. So start 32. Break it down into the factors.
Oh, yeah.
Yeah, 16 and 2. 16. Okay, keep going. I'm going to give it another. Okay. While we're working, we can also work backwards, guys. Girls, listen up. We can actually go the opposite way. I can give you a mixed number, and you can actually tell me what the entire radical would be. So, for example, if I gave you a number like 2 root 3, and I wanted you to switch that to an entire radical, guys, girls, I'm just working the opposite way. How do I get a number as a coefficient? What did there have to be inside the radical in order for that 2 to be in the outside? There had to be how many? 2 2's. So if I want to turn this into an entire radical, I'm going to have the 3 originally, and then how many 2's am I going to put in here? 2 of them. What is 3 times 2? 6 times 2 is? 12. How could I check to make sure that 2 root 3 is the same as root 12? Go to my calculator. If I go 2 square root of 3, I get 3.46. If I take the square root of 12, I should get 3.46. If I get the exact same answer, I know I'm correct. I want you all to try 4 cube root of 6. Tell me what that entire radical is. Go. Good. Perfect. Okay. So now, I want you to do that square root of the radical. Show me the radical. And I want you to put all of the prime numbers in that radical. Yeah, because there's 2 5, so 5 2's. Yeah. No. Oh, I want you to write it down 5 times. Yeah, I would. Okay. Is this still the square root, right? Yeah. Okay, so because it's a square root, I need you to find the pairs of 2's. How many pairs do you have? For every pair of 2's, write 1 2. Yeah, so you have 2 pairs here, so how many 2's are there? You're going to write 4, because 2 times 2 is 4. Good. Another way to look at it, 2 times 2 is 4. The square root of 4 is actually 2. Yeah, so you put 2, but then you have another one here, so then 2 times 2 is 4. These are done, cancel those out. You have how many left over? 2. So your answer is 4. Square root. Does that make sense? A little bit? Okay, try that one. Okay, so now you're working backwards. So you're working, if there's a 4 on the outside, how would that 4 had to come back?
Then you at least have 500.
The 3 is the cube root now. So instead of, so hey, here, Yaros, your cat. So here, guys, girls, nobody's got this done? Oh my goodness.
No, we were too busy reminiscing about your Backstreet Boys days.
It was a good rival lesson. Okay, if I have a 4 on the outside as my coefficient, how does this 4 get on the outside here. What had to have happened? This 4 had to be originally where? Inside. It had to be inside the radicand before. Because it's a cube root, how many 4s have to be inside here?
1.
It's a cube root, so there has to be 3. 1, 2, 3. Now all I do, because this 4 has disappeared, it's back into the radical, I go 4 times 4 times 4 times 6. 4 times 4 is 16. 16 times 4 is 64. 64 times 6 is equal to what? It's going to be a big number. 64 times 6. You all have cellular phones. I know that you can find this answer. Yeah? Oh, what's your question?
Does it, do you essentially break it down into a prime factor and
Your coefficient breaks down into the prime. After you break the radical into the prime factors, your coefficient becomes your pairs. So,
yeah,
right?
yeah, but the, and then you also break down the coefficient into prime factors, right? So you can get pairs.
No, you don't have to. The coefficient, like, are you trying to go backwards like this?
Is it 384?
You're gonna get a larger number.
I feel like it's good. No, it would be 384.
Yeah.
Give me one sec. I'm going to put a question up. I'm going to see what you're pushing me, okay? All right, 384. What? I need you to try another one. 5 square root of 7. Go. Tell me what that is as an entire radical. I need to see this one this time, though, okay? Sorry, what do you do? Oh, okay. That's the premise. Now that's the longer way. But that's coefficient. Like go from mixed to mixed. Really just slot that. Literally don't have anything. You just go 4 times 4. Does that make sense? So if you have a question. No, not for mixed or unmixed. If I had an example. I wanted to make this equal. I can do it with that. God. You said you could look at it.
Yes.
I could look at it this way. So now instead of yours, yeah, that's the whole point of that. So you did, right? In order for that 4 to actually get there, there were like 2 sets of prime. Yes, good.
There you go.
What's the answer? 175. How did I get 175? How many 5s do I put inside the radical? I put 2. Wonderful. How do I check to make sure my answer is right?
Yeah, pretty much, yeah.
How do I check to make sure my answer is right?
You flip it again.
Put it in my calculator. 5 root 7 gives me 13.22. The square root of 175 gives me 13.22. If my number is not identical, something is wrong. You need to go back and check your work. Right, Jordan? Alright. I have 2 slides for you. Okay? And I've got a couple minutes to go. So now we've conquered the beast of radicals. Is there any questions on radicals so far? You're going to get more of those questions with your take-home test. So I'm going to post these. I'll post the video and I'm going to post the notes on Google Classroom. So you'll have that to work with, all right? But just be aware that you're going to have a lot of these questions to go through. The next part, now that that's dealt with, is I want you guys to work on being able to identify where in fact these numbers are. Whether they are on, where they are in a number line. Okay? How many people, I go back to grade 9 when you did in grade 8, I think, your benchmarking activities. Remember, anybody remember how to do that or doing those types of examples? Basically what you're trying to do is estimate where a square root number is. Okay, or what that number is. We know that the square root of 36 is what? 6. There's no it's an even number because the what type of a square root is it? I just told you, it's a perfect square. Okay? But what about the example of 48? Is the square root of 48 a perfect square? No. But what we can do to guesstimate or approximate our answer is using benchmarking. Benchmarking is the skill of, or the strategy of taking a perfect square that is lower and a perfect square that is higher and approximating from there. What number, what perfect square is lower than 48? 36. The square root of 36 is equal to 6 and it's lower than 48. What is a perfect square that is higher than 48? 49. What is the square root of 49? 7. Approximately where could you say that the square root of 48 is going to be on a number line? It's going to be between 6 and 7. Which number is it going to be closer to? 7. So I would say a good estimate would be 6 point what? Like 9. Absolutely. Okay. Same strategy can be done for any of these terms. Okay. You're always looking for where to put that on a number line. All right. Another way to look at that is if I have my number line here, I know that the square root of 36 is here. The square root of 49 is here, and it's 7. Square root of 48 would be around this area, which means this has to be about 6.9. On your desks, I want you to tell me an approximation of the square root of 92. Okay? On a number line, give me the approximate number, without using your calculator, of where 92 is on a number line. Go. Kenzie, I need you to write something other than I heart Mary, like angry face and I heart Brian. Let's go. Let's go. Where is 92, root 92 on a number line? What? Show me what are the two numbers, and how would you use that using your benchmark?
I wish I had show me. I wish I had show me more.
Man, create Yep. I don't know. It's hard to say.
I just want to watch that Asian show where like the Asian family goes to French photos. Yeah. 18. I mean 81. I'll just get 80.
It actually is.
Alright, for square root of 92. What am I benchmarking? Mackenzie, what is a square root or perfect square that is higher than 92? You can help her. 100. Square root of 100. Jordan, what is a perfect square that is less than 92?
25.
Okay, yes, but the closest one that is lower than
Oh, the
92.
closest one?
Yeah.
84.
Close, 80,
81.
81. What is the square root of 81?
9.
Square root of 100 is 10. So the square root of 92 has to be between 9 and 10. If this is square 100, this is square 81. Where would you put square 92? Halfway, closer to 9, closer to 10. It's a little bit closer to 10. So what would you say? It's 9.6,
7.
9.7, that's alright.
Awesome.
Perfect. This concept works well with these examples here. I'm going to move this down a little bit so we can actually work with it. Okay, guys, girls, I've got I got one more slide after this. I want to get through this last piece. Okay? I can use the same number line concept when I'm dealing with fractions or rational and irrational numbers. Doesn't matter what. If I have 1 over 2, we all know where 1 over 2 is in a number line, right? It's halfway between 0 and 1. Okay? How I show that in a number line, I have 0, I have 1. It is literally in between. Okay? How I know that a third is approximately 0.333. Why are we throwing my markers around? Okay?
That was good.
Stop. I know that it's 0.3 repeated, correct? As a decimal. I know approximately where that is on a number line. How I can represent it so it's easier for me is I know if this is 0 and this is 1, I can break up my portions of 1 into thirds. 1/3, 2/3. 1/3 has to be here, and that's approximately a third of the way. Okay? Having said that, if I have 5 over 7, if this is 0, this is 1, how many sections am I going to have in the middle here? 7. 1, 2, 1, 7, 2, 3, 4, 5, 6, and then 7 over 7 here. I can't, where's 5 over 7 going to be? Yeah, it's going to be 5 over. 1, 2, 3, 4, 5. This is 5 over 7. If I were to ask for a decimal, based on what you see here, what would your decimal be? Okay, sure, 0.78. That makes sense? So I want you to prove for me, on a number line where, let's go 10 over 6, which actually works down to 5 over 3. Show me where 5 over 3 is on a number line. Go. 5 over 3.
What do you ever why did someone sit down?
Fractions?
No, like that.
Oh,
Yeah.
I said at the first of this class, I said this is very abstract stuff. The only reason why we're doing radicals and irrationals is thank you. I get polka dots. The reason why they do this is it's more accurate than this. And they want you guys to become more familiar with other numbers.
How do you do 5 over 3?
5 over 3, break it up into thirds. So, what's the difference here? Is this just from 0 to 1? Or is it actually from 0 to 2? 0 to 2. I'm going to break this up into thirds still. 1, 2, 3, 1, 2, 3. Right? How many, if I have 5 thirds, I've got 1, 2, 3, 4, 5. 5 over 3 is right here. If this is 1, 5 over 3 is there, what would you approximate that decimal as? 1 point, what? 1.8? Sure. It's actually 1.67, which could round to 1.7. Based on this number line, I can see you putting 1.8. Break it down into sections. That makes it easier for you to understand, whether it's 1, whether it's 2. Does that make sense? Okay, before the bell rings, I want you guys to look and try, hey girls, to tell me, I want you to order these 4 numbers, from lowest to biggest. Okay? The cube root of 115 is going to be an interesting one. I would recommend breaking that down into its prime factors and seeing if you can simplify it. Okay. But I want you to tell me before you go on your desk, the top row, from biggest or smallest to biggest, okay? That's another outcome, being able to sort through what each one.
and